Hello, everybody. My name is Florian Eigenmann. I'm your host today for this upcoming webinar. I'm with Andreas Hugi. He received his PhD from ETH Zurich, where he pioneered the first QCL frequency comms in the group of Jérôme Feist. And he's also, this technology is now crucial and implemented in our spectrometer, Iris F1. Please, Andreas, go ahead.
Thank you for the introduction, and also a very warm welcome from my side to this second webinar of today on the progress on dual-com spectroscopy with QCL. So let me start right away with the agenda. First, I want to give you a presentation of the Iris F1, the product as it stands. Then I'll give you a first sneak peek on a new product which will launch in the foreseeable future, which is basically the emitter module only. So it's the heart of the instrument, which allows new application spaces to be pioneered. Then I'll give a short introduction on dual-com spectroscopy and what it actually means in terms of technology and how it works. Then I'll give a short introduction on a new operation mode that we introduce in our instrument, featuring millisecond time resolution. And then I'll go to the latest laser development updates, and at the end, I'm very excited to actually talk of some of the application examples which we've been able to realize with the Iris F1. And we finish off with a question and answer session, and we'll keep it open until we answer all the questions from you. So, Iris F1 really enables fast infrared spectroscopy. It combines high speed, high brightness, and the parallel multi-wavelength capabilities. The high speed turns into a customer benefit because he can basically measure fast processes, so kinetics or high throughput measurements. The high brightness turns into the advantage that they can measure optically real-life samples. This is especially useful for liquids, which we'll see in one of the applications later on as well. And the parallel multi-wavelength capability allows customers to actually measure complex mixtures and processes. If we look and we combine those three characteristics together, the kind of measurement that can be achieved with such a dual-com spectrometer is shown on the left side here. You see on the x-axis we have the wave number axis, as in a traditional spectrometer. Here we cover about 50 wave numbers, around 1215. And on the y-axis you see the time axis. Here we go all the way to 15 milliseconds. What you can then basically see here is a protein kinetic reaction that we can follow on a microsecond time scale up to millisecond time resolution. The brightness is due to the laser source. So if we compare with traditional FTIRs, which are glow bar based, we have orders of magnitude higher brightness. And if we compare it with external cavity QCLs, we of course have the same kind of source inside, so the brightness is in the same order of magnitude, but we feature a much higher time resolution, really putting the instrument in a unique spot compared to the competitors. We say that the QCL frequency comm is a broadband source, and we cover around 65 wave numbers. 65 wave numbers, if we talk to spectroscopists which use laser spectroscopy, they're used to about 1 to 2 wave numbers with a DFB, for example, so 65 is a big number. On the other hand, if we talk with people like working with FTIR, 65 is a narrow number. So it's a broadband source, but it is narrow band compared to FTIRs. And for this reason, we had to come up with a solution enabling our customers to address different bands. That's why we developed this easily exchangeable laser module. Basically, it allows to buy different modules emitting at different wavelengths. So for example, one module can emit at 6 micron for amide 1, and the second one could emit at 8 micron if you want to measure in the atmospheric window. And it's quite easily to exchange those lasers. So basically what you're doing is you just lift it and you place it back. And the system is engineered in a way that if you put back the system, the laser module in the system after you removed it, your system will stay aligned. So there's no realignment needed. The detectors that we feature in our instrument are two high-sensitive thermoelectrically cooled MCT detectors. The important point here is that you don't need any liquid nitrogen to operate the instrument, and everything is integrated. The instrument that we basically offer, the IRIS-F1, is combines 3 different parts. So first, we have on the top left side, you see the box. So this is really the spectrometer. It's very similar to an FTIR spectrometer. Then you see the rack, which we offer, which we add to the instrument. We have the electronics here. We have the data treatment computer at the lower part, and we have a chiller, which is used to basically stabilize the laser sources. Furthermore, we also add a computer to drive the whole instrument. And the software we try to keep intuitive and simple. And the most important thing, we try to keep it, export the data in an open format in a way that you can really use it in your program that you're used to. So if you like to use MATLAB, you will be able to use it. If you like to use Python or LabVIEW, you'll also be able to use it in a seamless manner. The accessory, if we look at the accessories that we offer, so the first thing is that we engineered a very large sample compartment to easily integrate your experiments. The sample compartment or the door of the sample compartment can also be taken away. This is sometimes necessary in some experiments if you need access from the back, for example, which we'll see also an example that we had to do this for one of our experiments. Here we see, for example, a reflection configuration we had to do for one of our customers. And you can see that the large sample compartment really helps to do some simple alignments and some simple optical elements to align your system on your sample. You can also do more traditional transmission measurements, or ATR configurations also work very nicely. For example, we have used SPECAC ATR Golden Gate configuration to measure the reaction of UV curable glue. And we'll see the results at the end of the talk. But what is important here is that you see in the back, we actually had to remove here the cover to be able to reach the experiment with those optical fibers, which basically bring in the UV light to cure the glue. So let me switch now to this sneak peek. So it's the first time that we actually officially show this new product that we are soon launching. It's an emitter-only module. It is aimed at people who want to integrate a dual com source in their own instruments. So it really is a dual com source. Basically, you see the 2 holes in the front, and you get out the 2 laser sources, and we offer it in a way that it's compatible with our flexible exchangeable laser module. It is important to say that people who buy such an emitter module, they really have to know more about laser physics and how to align systems and how to handle, for example, feedback and issues we have been dealing in the IRIS-F1. So it is really for people who want to use it and integrate in their own instruments or in their own experiments if the IRIS-F1 is not suitable. Let me now switch a bit to the dual com technique so that you have an idea how the instrument actually works and how we reach such time resolutions of 1 microsecond. So a dual com spectrometer basically consists of two optical frequency comb that you see here on the left and on the right. And each optical frequency comb emits a broadband coherent source. So compared to a traditional laser source where you have one optical frequency, so one color, a frequency comb emits hundreds of optical frequencies in parallel at the same time. So if you then probe your analyte here, shown here with those molecules, you basically get your spectral information in parallel. Now, usually if you have a broadband broadband source, you need to have some sort of a dispersive element. So in an FTIR, this is usually the Michelson interferometer, which does this job. In a dual comb spectrometer, it is the second laser source which takes over this job. And basically on the detector, you generate an interferogram similar to an FTIR, which you can then transform into a spectrum, as you know from an FTIR. So a bit more technical here. I think this is the most technical slide that we have in the presentation. So we have here the two lasers again. Laser 2 probes the sample here, and the laser 1 is the one which acts as dispersive elements, and both are configured to be focused on the detector. Now, if we look at the optical spectrum, we said we have a multimode source. So the laser 1, here denoted in black, has optical frequencies, and they're all spaced by a certain repetition frequency, FR. The second laser on the left side, laser 2, you see is noted in green, and it has a slightly different optical mode spacing, FR prime. And if you see what happens then basically is that on the detector, you generate neighboring modes, generate a beating. So it's an interference pattern between two modes, and you generate a RF frequency beat node at a lower, in the RF domain. And the neighboring pair, since you have a slight shift between the lines because of the different mode spacing, generates another line. And basically what you generate here is really a direct optical to radio frequency link, and you can then recover this signal by a simple Fourier transform, and you get your optical spectrum out. And the most important part, or the most important feature here, is that you have really no mechanically moving parts, and that makes it so fast compared to FTIRs. The dual comb spectrometer that we're using is driven by quantum cascade lasers. They were basically, when I was doing my PhD in the group of Jerome Feist, we were able to show that the first time in 2012. Together with my colleague Gustavo Villares in 2014, we were able to the first time show that it can be used in a dual comb configuration. And since then, we have basically been working to integrate that in a commercially viable product that is that can be used by people who have less laser know-how than we do. The key characteristic of quantum cascade laser frequency combs is that they operate in the mid-infrared region, so you can access the fundamental low vibrational bands. It is multicolor operation, so you basically have not one single wavelength, but hundreds in parallel, and you have high emission powers. We're talking here of hundreds of milliwatt. And the coverage is about 40 to 70 wave numbers. Now, this dual comb, our instrument can be operated in different operation modes. The data that I've been showing you before, where we had this time-resolved data of a protein reaction, was recorded with this so-called time-resolved mode. So the way this works is that you have a number of samples that are acquired continuously over a 16 millisecond, which is the default of the instrument. Then you trigger your experiment, and everything which follows the trigger, you can then basically follow the reaction, the chemical pathways that you want to record. And the pre-trigger samples are used as a reference. And you can acquire this at several times, n times, as much as you want, and they're basically then co-averaged to improve the signal-to-noise ratio. So this is this time-resolved mode, which allows to have very fast time resolution down to microsecond. Then the second mode is the static mode, which is more similar to traditional FTIR, you basically measure a background before you put in the sample. Then you put in the sample, and then you do a sample measurement. So you lose this time resolution, but you enable different kinds of measurements and more similar to FTIRs. I think what is important to say is that those 16 milliseconds have been improved on our side. So we offer now an option to upgrade this to do 256 milliseconds. So you can really continuously monitor kinetics up to 1/4 of a second. The second thing which we'll offer in a software update in the coming days is that we significantly reduce this acquisition frequency dead time. So at the beginning, if you measured, or at the moment, if you measure 16 millisecond time slices, you have to wait, or the maximum acquisition frequency is 0.4 Hertz. Now with this new mode, we managed to improve that by a factor of 10, and you can actually measure at 5 Hertz acquisition frequency. We do this by having a buffer, which we then write in the data as fast as we can before we process them. So in the standard configuration at 16 millisecond integration time, you can, for example, have 28 of those buffered acquisitions. But you can, of course, also decrease the integration time, let's say to 70 microseconds, and then you have all of a sudden 7,364 acquisitions. So it gives really a lot of flexibility in terms of your experiment. Here we have an example how we actually follow a different kind of reaction, which is happening on the millisecond time scale with this buffered mode up to 3 seconds of integration. So we have operated the instrument at 40 millisecond repetition with 1 millisecond integration time, and we can see we can very nicely fill this gap. So basically, the time resolved mode offers operation from microsecond to 256 millisecond. Then we have this new buffered mode, which allows millisecond to hundreds of seconds of acquisition, and we have the static mode, which is for acquisitions which take more than 2 seconds, basically. Let's go on the laser availability. So since the start of our company, we have been constantly working to enable new applications and to have a larger wavelength laser availability. So as you can see, we have lasers around the amide-1 band. We have lasers at 1650, at 1620, and at 1760. And we have a laser which is in development, which will fill the gap between 1760 and 1650 soon at 1710. Furthermore, we have lasers which are around 1200 and 1000 wave numbers. And we are also in development of a laser at 1260 wave numbers. The important message that I would like to bring along here is really that we want to develop laser wavelengths which are important for applications. So please come to us if you see that we are missing one certain part that you absolutely want. We're always listening, and we try to adapt our laser development roadmap according to customer needs. Just an example of a new laser which is emitting at this amide-1 band. So we have, if you see the wave number, we really we cover from 1680 to 1610. We have laser parameters of 0.5 wave number spacing, more than 200 lines that you measure in parallel. So we really cover more than 60 wave numbers of wavelength. Also, the profile, the envelope is quite nicely flat compared to previous lasers. But you might say, oh, but there are some holes here in the middle. But those holes, they are actually nothing else than water lines. So we're actually doing spectroscopy already just with the bare spectrum of the laser. I think at this point, I would like to point out that the instrument is, of course, purgeable, and then you can get rid of those water lines as in a standard FTIR. So let me switch over now to the applications. The instrument finds actually more and more different application spaces. One of them is, for example, protein analysis, where we have where you can look at protein folding and unfolding, or protein reactions in general. Then we're looking at combustion reactions. So there we're looking at irreversible reactions of shock tube or rapid compression machines. We do have some customers which are interested in process monitoring in pharma. The main driver there is low concentration measurement in strongly absorbing matrices. Photochemistry is always interesting because you basically have a light-induced chemical reaction, which is fast. Polymer chemistry will also have an example that I want to show you. And some of our customers are also doing trace gas analysis with our system. So let me go a bit more in depth with some of those applications. In combustion, combustion research is happening. A lot of the combustion research is happening on so-called shock tubes. So those are, you see a picture there. They are quite big tubes, and they basically ignite an analyte that you want to follow the combustion through a shock. So you build up a shock on one side of your tube, and then it propagates through the tube and it ignites the combustion. And you want to measure this to basically to understand the chemical pathways and to optimize such reactions. It's a very nice example because, because it fits our instrument nicely. The dynamics happen at a very fast time scale, so we're talking microsecond to millisecond. It is non-repeatable because each shock is slightly different, so you really need to have sort of a single shot measurement, which the iris provides. Then you are dealing with multi-species because you're basically burning something, so by definition you will change something. So you're in need for a broadband spectroscopy tool, and you want to have quite strong lines because the high pressure actually makes optical penetration challenging, so the laser helps on that side as well. Here we see a picture of my co-founder at King Abdullah University in the group of Amir Farouk, aligning the system on a shock tube there, and it shows nicely another example where we actually guide the beam outside of the instrument through the shock tube on an external detector, and we feed back the signal on the instrument like this. So that's also a kind of a configuration which is possible with the instrument, and it shows once more the flexibility of the instrument that we offer. So another measurement on combustion has been done in collaboration with the group of Ronald Hansen and at Stanford University. And you can see here basically the kind of real measurement you can get with such an instrument. It's very nice. So basically you see the shock arriving. So at the beginning, you see this increase that you see the shock arriving, and you see the spectrum you see the propane spectrum, and then you see that the intensity actually decreases. So that's when the propane disintegrates into smaller radicals until the point that combustion kicks in. That's at this moment here, and we form water and CO2. So with this instrument, you can really follow this reaction in a single shot. If we look a bit more closely at the experiment, which has been carried out at Stanford University, we wanted to basically show that even under those very hard conditions, so a shock, vibrations, our instrument is capable of measuring the correct concentrations. So in parallel to the dual-com spectrometer, we also measured with ICL lasers at 2 different frequencies. First, the propane concentration, as well as the water concentration. And on the lower right part, you really see that the dual-com measurement, as well as the reference measurements with ICLs and the model, agrees nicely and really proves that we are measuring the correct concentrations with our instrument. Interesting is also to see the comparison with external cavity QCLs. So external cavity QCLs are pushed also further and further for high time for faster scanning rate to improve the time resolution of those instruments. And we basically also benchmarked commercially available external cavity QCL with our dual-com source. And on the top left, you see that the fastest time scan rate that the external cavity could reach was 2 milliseconds. And if we compare the signal to noise of an external cavity and our system, we see that we are actually much better compared to them. Now, I think to be fair in the comparison is to actually also point out that where the external cavity still is more advantages is that they have a bigger spectrum than we're having. But I'm confident that with future laser development, we'll actually reach similar bandwidths as external cavities. Also interesting is, for example, if you want to do reaction kinetics at high temperatures, so this is the lower right graph, and basically the higher the temperature, the faster the pyrolysis process takes. And you can see that the dual-com system can actually go to much higher temperature compared to the external cavity system, simply because we have a faster time resolution compared to an external cavity. The next application I want to talk about is polymer chemistry. We have been doing those measurements in collaboration with DLO, which is doing industrial adhesives. So basically what we want to measure is this reaction that you see here on the left side in the video. So you see that basically we have this UV curable glue, and then we have a UV lamp which turns it on, and we want to follow those reaction kinetics, reaction pathways with our instrument. Nowadays, when researchers at DLO use conventional FTIRs, they basically get access to the before and after curing. So you see one band at 1648 wave number and a broader band at 1635 wave numbers. Those spectra were measured with our instrument, but they agree nicely with the reference spectra which were provided by DLO. Now with our instrument, of course, you get a higher time resolution. And on the left, you see what kind of measurement we get. Basically, we used here this buffered configuration, which I was explaining. So we have every 40 milliseconds, we have a spectrum. And each spectrum we integrate for 1 millisecond. And the first thing you see is that we actually can identify 3 isobestic points at 1660, 1644, and 1616 wave numbers. So you already get more information into your chemical pathways. And if you then basically follow the peaks, how one forms and the other one decays, you can then see that you actually need some second order kinetics to understand what's going on. So you get much more insight into your chemical pathways compared to FTIR data. The next application is the process analysis of optically dense samples. I already said that the high brightness helps to improve the penetration. So this is one of those examples. We were contacted by a pharmaceutical drug company, which tries to replace GC with an FTIR in their pharma production process. And the target for the analyte that they want to measure is 0.1 milligram per milliliter, but the current detection limit they can reach with commercial FTIRs is 2 milligram per milliliter. So our solution is really to go through to direct absorption spectroscopy, and we managed to improve the path length and have now path lengths of up to 100 micrometer, and we were able to show detection limits of 0.05 milligram per milliliter. If we look at the measurement, what is really what always amazes me is the fact what we actually can get out from the bulk absorption. If you look at the bulk absorption on the top left, you see we have absorbance units of 2 to 2.5. However, if we do a subtraction of the matrix, you see that the analyte peak starts showing up. And if we do a simple baseline correction, we get a nice spectrum, and linear regression, we can then basically show that we can repeat repetitively and each time measure at very low concentration limits down to 0.05 milligram per milliliter. The last application I want to cover here is protein structure analysis. So in the mid-infrared, you have some characteristic protein bands, which can be probed with spectroscopy techniques. So the most known band is the amide 1 band, which addresses the CO stretch. Then you have other bands such as the amide 2 and all the way to the amide 3 band. What is important is that IR absorption can give you information on the secondary structure. So you know if you have, for example, a beta sheet, a random coil, an unordered protein, or an alpha helix. Those measurements, this was really one of the first proof of or application feasibility tests we have carried out with our instrument, and it's the bacteriorhodopsin photocycle, which we measured together with Professor Tilman Kotke from Bielefeld University. So bacteriorhodopsin is a transmembrane protein. It sits in the membrane, and if light hits the protein, it undergoes a conformal change. And when it relaxes, it basically pumps a proton across the membrane, and you basically build up a chemical potential, and it acts as a photosynthesis process. And those changes can be measured by optical techniques. Now, this has been done traditionally with step scan FTIRs. So they excite this molecule or this protein 20,000 times. And what we have shown basically in this paper that the iris F1, we can already reduce those kind of repetitions to 500 to get the same signal to noise ratio. And also one thing which is interesting is that we can again increase the signal by increasing the thickness of the sample. So basically we need much lower repetitions to get the same signal to noise ratio. But you might say, yeah, so what? I mean, it can be done with an FTIR. However, really the true challenge or the true new development for this kind of field is that you can do a single shot, because many proteins, they are not as long-lived as bacteriorhodopsin. Bacteriorhodopsin, you can undergo the cycle easily 20,000 times. On the other hand, you have many proteins which might age. So you might be able to average 10 or 100 acquisitions, or some of them, they're basically a single shot. So a protein undergoes one reaction and you cannot go back. So for this, you actually need a single shot instrument. And even with a single shot, we were able to identify microsecond lived states. With this, I have basically finished this webinar. I would like to highlight the next webinars, which are more application focused and which go deeper into those applications which I've been discussing. So at the end of the week, we have another webinar on curing processes. Then in July, we have a webinar which goes into detail on the combustion processes. And at the end of July, we'll have a webinar which focuses on biospectroscopy applications. With this, I would like to thank you for your attention and show some of the upcoming events, because we're traveling quite heavily the coming days. So if we're near you and you would like to meet us, we're of course always eager to meet you, either at the conference or at the trade show, or maybe also visit you on site. So please contact us if we're close by, and we'll visit you basically. And with this, I think I would like to open the questions and answer session and give over the word to Florian.
Thank you, Andreas, for this really nice talk about QCL frequency comps. Please use the channel with the tab with the questions tab, and write your questions right away. we have already on some other channels some questions which showed up, and I start quite directly as a background. I have a lot of information about FTIR spectroscopy. Andreas, what is actually the main reason why you can actually make such fast spectral resolution and temporal resolution? I mean, so high spectral resolution with that temporal resolution.
Yeah, it's true. So basically, what we haven't touched yet is the spectral resolution. So the instrument really features 0.0003 wave number resolution, and that's basically we have a laser line, discrete laser line, and each one is very highly resolved. So that's the reason why you basically get the resolution of a laser-based instrument. And the temporal resolution is really from the fact that the interferogram is recorded basically only electronically. So you don't need to move any mirror, you don't have any moving parts. Also, if you compare with an external cavity also has a rotating mirror in the back, and this in the end will always limit the speed they can reach. So our system will always be faster than any mechanical system.
I think that's very impressive, especially the application which you showed about combustion, and of course also the curing one. I have another question which showed up. One especially about the emitter unit, which you presented, I think, the first time here in public.
Yeah.
Is there something you need also additionally when you do like chemical imaging?
Yeah.
Is there some additional thing which you need?
It's a good question. So the emitter unit we developed for a customer which only wanted the emitter unit, but we're actually already looking into some customers which want to do imaging with this. And basically what we offer is, of course, also a collector unit with it, because we don't want that people have to re-engineer the whole detection system. So you can have an emitter and a detector unit, which you can then basically integrate, for example, in your microscope, if that would be the goal. Yeah.
Great. So the floor is still open, and you always can send us actually questions also on info@irsweep.com. Probably another question which we have here is you showed a little bit the laser availability list, which is very interesting, and I think it's growing all the time. We have seen 1200, 1650, 1760, 1710. What is the next one? Where does this journey goes?
It's a good point. So I think so I don't want to name too hard numbers here, because it is always it's always driven by of course where the biggest drive is from customers. I think one wavelength which we're missing and which we should cover in the foreseeable future is the hydrocarbons at 1450. That's for sure a range. And I think it's also important to say that we are pushing the boundary on the high wave number side, so the 2000 and above, through a project in collaboration with laser manufacturers. So I don't want to give any numbers, but basically that's what we were trying to do.
Okay, and the brightness, you spoke a little bit about the brightness, is now 60. Yeah, is there a possibility to push that to 100 in the near future?
It's a good question, because just today we have had first lasers which really have, I think, 100 wave number span. We guarantee when we offer a laser module, we guarantee 60 wave numbers, because that's basically what is the most achievable. But we have seen now 100 wave numbers, and I think that can be pushed. I mean, the bandwidth of QCLs is larger than 100 wave numbers, so I don't see a technical reason why we shouldn't reach that.
Great. So thanks, Andreas, again and you all guys for joining today's webinar. We will have another webinar, several webinars lined up. The next session about applications, some successful application, will be on Friday. So we have a webinar at 10 a.m. and 2 p.m. Central European summertime. So be ready for that one if you're interested in a little bit more in those applications which Andreas touched already. And you have also the possibility to go online, like on www.irsweep.com. or send us an email at info@irsweep.com. Thanks, everybody, and enjoy your evening. Best.
Thank you. Have a good day. Bye.